Hey guys, I'm Dillon and I'm joined by Avi, and today we're going to be talking about getting up to speed on real-time machine learning. A bit about us. For me personally, I've been with Databricks for a little over 5 years, and basically spent that entire time working directly in the field. So mostly working with customers, including startups that are kind of born in the cloud, fully focused on data and AI as their company strategy, to large Fortune 500 and above, very large companies that are also trying to figure out how to become more data and AI centric. So spend a fair amount of my time working directly in the field, and when I'm not doing that, I also help lead a group of folks, and this group is basically people from all over the world working at Databricks that are interested in being experts on things like data integration, ingestion, and transformation. So think streaming, some Databricks products like Delta Live Tables, for example. And what I'm actually really interested in and excited about to talk about today is I'm really interested in what are the ways that we can use different streaming frameworks to enable more use cases. So I think from my past 5 years working at Databricks, I would say my experience is that most people sort of see streaming as this way to, at very low latencies in real time, get data from one place and to put it into another place. And there's actually all sorts of value that that streaming can provide. And I think that there's usually sort of like this gap that I see with a lot of the customers I work with, where you have people that know streaming really well, and then you have people that know data science really well. And I think the hardest part when you're getting real things into production and where you need low latency, it becomes very kind of challenging to understand what are all the different ways that you can add value. So I approached Avi, who's more of a data science expert on my team, and kind of brought this problem up, and that's why we're here today. Avi, do you want to give a bit of background about yourself too?
Thanks, Dillon. Hey guys, I'm Avi Sooriyarachchi. I'm a solutions architect at Databricks. I've been here for a lot shorter time than Dillon, but I've been here for like 2 years. And my entire time here, I've been focused on working with customers to build machine learning based systems. And at a surface level, it all seems like just training models and deploying them. But if you look at the bigger picture, it's actually more of a software development problem with various moving components, and you need to kind of take a look at things at a very granular level and at a high level at the same time. My particular interests lie in kind of building systems, leveraging foundation models. So when you think of foundation models, you can think of them as large language models or kind of generative models, or essentially any kind of machine learning model that has been that's large enough that it can be adapted for different kinds of workloads. And I also have interest in kind of combining those sort of models with traditionally not so leveraged architectures like streaming inference to build systems for businesses to use. Because at the end of the day, it's not just about the machine learning process. It's about kind of building end-to-end systems that serve the business need. And to do that, you need to have both the data engineering part and the machine learning part, as well as the overall architecture kind of built in a proper way. So that's kind of how I got involved with Dillon in his work, to combine certain aspects of stream processing with machine learning, both on the inference side as well as the feature engineering pipeline side. So it's really interesting work, and I hope what we talk about today is going to be useful for a lot of you guys.
Cool, thanks, Avi. So just taking this from the abstract, so what we're promising you. So you know what you're signed up for, and also if you're watching this on on demand, you have an idea of what we're going to be talking about. So first, obviously, we're going to talk about what's the value of real-time machine learning. What does it actually mean? At first glance, it's like, okay, I was a little bit worried. Does it sound like we're just taking two different buzzwords and mashing them together? And there's obviously like a lot of use cases already that do this. But I think what really we also want to talk about is, in addition to the value of real-time machine learning, how do you actually prioritize ones that make sense for the organization that you're working in, right? and how valid is it? How can we actually show to the business that it's worth prioritizing beyond just training a model in a notebook and it scores pretty well, but like, what do you actually need before you even get to that, to making it run in production? So how should you actually be prioritizing all of the different potential use cases that you learn as you come out of this talk and go back to the different businesses that you're supporting? Then we're going to talk about what are the different patterns and architectures and sort of repeatable patterns that Avi and I have seen over and over again with the different customers that we work on at Databricks. And I think it's actually interesting. There's some patterns that we're going to talk about that I think a lot of people have sort of, when they first think about, okay, real-time machine learning, that means maybe really fast inference, for example. But there's actually a lot of different parts of the patterns that we don't talk about as much, and we kind of want to start to show, hey, this is what's repeatable, this is what you can use for any kind of use case. And then finally, what's the value of a streaming framework in that pattern? And streaming is more than just for feature engineering. There's actually a couple different areas that we'll talk about. And how would you go about choosing that streaming framework, especially if you're coming from maybe a data science side where you don't have a lot of background in streaming. So just to start things off, I want to talk a little bit about what I think of, or kind of what Avi and I talked about, what we kind of think of as like the sort of perfect example of real-time machine learning, and that's fraud detection. So Avi and I actually, we do a lot of work with retailers and CPG, like consumer packaged goods companies in the US. And this is, when we work with e-commerce, we see that fraud detection is basically like a table stakes problem that you need to solve. So just thinking about fraud in e-commerce alone, before we even get into all the different other kinds of fraud out there, roughly about 3% of e-commerce transactions in the world are actually fraudsters trying to do identity theft or steal some goods and resell them or something like that. It's actually kind of funny that I'm bringing this up. I actually happen to be traveling pretty close to I'm actually based in the East Coast of the US, but I'm actually traveling closer to the time zone where we're giving this talk, actually in Europe, conveniently for me. And literally just 2 or 3 hours ago, my wife's credit an e-commerce account that she had was hacked, and someone was placing a bunch of orders. So I thought it was kind of funny, especially while we're traveling. It creates obviously a pretty bad customer experience. So there's obviously bad customer experience when you get hacked, but also when an e-commerce company says that you're a fraudster when you're really not. And what we're actually finding as a general trend, this is data from last year, is that over the years, actually more money is being lost to fraud, but also e-commerce companies are more often rejecting real orders, and that's leading to a lot of chargebacks, a lot of disputes, and overall, more customer churn. So we're seeing more false negatives and false positives. And just to even get into the e-commerce world, you basically have to spend about 10% of the money that you're making, right? So 1/10 of your revenue has to go to fraud detection. What we're seeing on average, typically a merchant is spending about that much, which is really kind of crazy when you think about it. The reason why we think fraud detection in general, and not even just within e-commerce, but any sort of anomaly detection where there's some sort of adversarial agent on the other side of it, right? So think about like network intrusion detection or kind of other cybersecurity use cases as well. These are sort of the perfect examples of the challenges that we run into with real-time machine learning, because you're in this sort of cat and mouse situation, which I, as a technical person, think is really kind of an interesting thing, because as soon as you make a model that's good enough to stop the current method of fraud, the fraudsters or the hackers or whoever they are, they're going to turn around and come up with a way to game your model, and then you're going to have to make a better model. So when you really zoom out and think about that cat and mouse game that we're always having to work on, you're basically looking at some sort of data drift, right? So concept drift. Of course, we can also talk about, there's also feature drift and label drift, right? So how much of it is the actual covariance versus, the change in relationship between the features and the labels. But this is sort of like a classic concept drift, right? So you think about concept drift, typically when we think about concept drift, it's usually some sort of like market forecasting sort of situation, right? Like we have a forecasting model for Clorox wipes, and then COVID happens, and now we have to retrain our model because there's been some drift in the concept and relationship between the different variables. So, but what makes this a little bit different than that kind of concept drift is that we have to be able to detect it very, very quickly. And when we do detect drift, we need to be able to put a new model out into production as quickly as possible, because any amount of time that we're waiting to put a new model into production, we have a very large amount of revenue at risk to this new fraud, this new kind of form of fraud that our model in production is not finding, right? And we can't have any downtime, right? We can't just stop detecting fraud for some period of time, because now the whole business goes down. So we need to be able to detect drift very quickly. We also need to be able to respond to drift very quickly. And a little bit outside the context of this talk, because we could do an entire talk just on this, is like different forms of adaptive learning, right? So maybe more naively, we'll just put a new model into production on some fixed interval, but then you kind of start to think, okay, we probably need some sort of monitoring if we don't have the labels, right? So maybe we for a false positive, we'll probably know from the customer that we'll get that ground truth. But if it's a real fraud, like what happened with my wife earlier, she did report the fraud to the company, and so maybe they have that label, but if maybe she missed the fraud, they'll never know. So you kind of have to do some monitoring on the features, and then there's kind of more and more kind of advanced and more sophisticated ways to do retraining in response to that drift. So we're not going to get into all the nuances of this kind of field of adaptive learning, where you're actually like detecting changes on the fly and maybe changing the model on the fly. But what I think it, just kind of bringing that up, that sort of that big business problem that we need to solve, really shows it kind of makes you appreciate that what we're looking for in a system to solve this is something where we can basically take anything that we have in batch and then run it in streaming, and vice versa, right? So I might have my feature engineering pipeline that I need to retrain the model, excuse me, but I also need the features that are running in production to be logged and monitored, and there needs to be some sort of parity between the feature pipeline that's maybe running in a stream in production and the feature pipeline that I'm using to batch retrain models, or maybe incrementally modify models in some way. So what you're starting to see is that we need some sort of general purpose way to go between batch and streaming, and potentially kind of like dial that knob of latency to deal with all of these kinds of problems. And then the final bullet point is just scoring latency. I think most people, when they think real-time machine learning, before we get into like fraud detection and all these other interesting problems that we need to think about, usually it's about, okay, that means that my scoring needs to be very fast. So I need to be able to make inferences at some low latency. And that's of course also the case with fraud, because if I place an order in an e-commerce situation and it takes me 30 minutes to be able to even place the order, or even 10 minutes or even 1 minute, depending on how much of an impulse purchase I'm making or what's going on there, that actually has a direct impact on my customer experience, how fast the fraud inference can happen. To give another example, right, it's highly dependent on the business use case, even within fraud. So like to give an example, I think about sports betting, right? So companies like DraftKings and FanDuel, they make a lot of money off of in-game betting, and there's all sorts of different ways that you can try and hack or misuse the in-game betting. But if you're placing a bet right before a play happens, maybe with even a couple seconds before a play, they need to do fraud detection on that, so that they can basically put that bet in, and if you're not able to put bets in even within seconds, maybe even sub-second, then that's going to have an impact on customer experience as well. So if you zoom out everything I just said, I know I kind of went deep into some of the problems that we run into just with this one example use case. What it begins to paint the picture of is that when you're addressing different kinds of use cases across your entire company, right, the latency requirement, right, or what kind of data freshness you need for that use case is sort of like a sliding scale, right? On one extreme, you have like I think of as like the original consumer analytics use case, which is surveys in the mail that go out every couple months. And then on the very, very, very other extreme side of the spectrum, I always like to give the example of hedge funds who are doing high frequency trading. And there's actually rules. I always think this is an interesting example of that extreme end when we're talking about nanoseconds and microseconds and things like that. There's actually rules around how long the Ethernet cable can be between the stock trading server and the hedge fund server, because if that cable were to be a couple feet shorter, maybe the hedge fund tips off the person who's cutting the cable, they're going to see the market first, and they could be making billions of dollars because they're getting like even just a nanosecond of visibility, right? So, but my point in kind of giving those extremes is that what we typically do as an industry, and from my experience having spent the last 5 years at Databricks, is that what we'll say is, Anything that's like hours, maybe 30 minutes, maybe 15 minutes at best, we're just going to call that this thing called batch. And then batch is going to be the way we've always kind of done ETL. Maybe we can just do queries off of a data warehouse, kind of the way that we've figured out how to do this with databases for a long time. Then everything faster is this niche thing, and you need a special sort of framework, streaming, and then sometimes streaming kind of, it's kind of intimidating, right? It has a lot of like complex connotations around it. And then there's like this in between where it's like maybe multiple seconds, maybe minutes, where it's sort of in between, and it's not true real time. Maybe we call it near real time. And then sometimes I would even say, like from my experience, sometimes near real time has almost a negative connotation around it. But what I would actually argue is that that's a limiting sort of way to split the world. I think it's actually a false dichotomy. And as we'll see in a little bit when we get more in the weeds around how streaming works, there's actually a lot of value that a streaming framework can provide, even to use cases that only need hours or days, right? So there's actually, I've worked with customers at Databricks that deploy streaming. They get a lot of value around some of the default tolerance that streaming gives you, and they're only running it on maybe once an hour or maybe even once a day at midnight. And I would also argue, as we already saw with the fraud detection example, that middle area where we're talking maybe seconds and minutes, there's a lot of business use cases that actually don't need anything better than that. So there's actually, very few use cases that need milliseconds or better, and when they do, usually they're highly specialized. And like as we saw with the hedge fund situation, they're going to need something kind of more customized anyway. And that brings me to my next point around how we think about prioritizing use cases. And this is something, again, like just based on my experience working with a lot of different customers at Databricks, this idea of being more data centric around how we prioritize the different use cases. And so what we do on the right-hand side is we have some different use cases, right? So fraud detection, maybe as we saw with the sports betting example, we have different kinds of desired data freshness. Maybe we need seconds for our feature freshness, for example, if we're going to be able to get any value out of this. What we need to do before we even fire up a notebook and start training different models on the data we already have, what we actually need to do is figure out how fast can we get those features when this model is in production. And we need to figure that out before we actually start the use case. So I think it's really important to think about the data characteristics and the data availability, right? So the characteristics are also like, is this an append-only stream? Does the web team that maybe has all of the clickstream data that we need for the fraud detection model, do they have a Kafka topic set up, or are they just dumping the data into an S3 bucket at the end of the day? My team as the data science team, am I going to be able to convince them to set up a Kafka topic? And if I can't, there's no point in even going down that use case, right? So I think it's kind of obvious, like people kind of roll their eyes when I say the data freshness, the desired data freshness can't exceed the data availability. But in practice, I actually see this all the time, and I think it's just another way to think about how do we actually prioritize these use cases, right? So even thinking about characteristics like, is the data append only? Are we dealing with change data coming from like a ERP, right? Like an enterprise resource planning? Do we have to deal with SED type 2, right? Those are all kinds of things that when we're doing in the training phase, we don't have to care about. But when we put this into production, if we don't have the right infrastructure and the right data engineering in place, and we're not sure that we can do all that ingestion, basically the project's going to stall. And I really do believe that this is a big reason why a lot of machine learning use cases never make it into production, right? All right, now I'm going to hand it off to Avi for a little bit.
All right, thanks, Dillon. So we'll be kind of switching back and forth every couple of slides, just so that everything is cohesive. But yeah, Dillon talked a lot about some of the finer as well as high-level details about the intersection of streaming and machine learning. But I want to kind of take a step back and just take a look at a classical understanding of machine learning and how that lends well into that blends into this conversation about deployment patterns and the timeliness of features as well as inference. Now, I know there's a lot of buzz about generative AI and stuff like that, but at the end of the day, like I think it was Judea Pearl who said, machine learning is just pattern matching. You extract patterns from data and use those patterns to make predictions on new data. And the way you frame it is going to be what decides whether it's going to be a generative task or a pure inference machine learning classical task. Now there are a number of caveats and nuances to this, but at a high level, this is accurate. It's also important to dig a little deeper and understand the machine learning lifecycle. Now, we are talking at a open data science conference, and you guys might be very familiar with the process, but at the same time, it's worth kind of level setting. Imagine you're a data scientist, which you probably are if you listen to this talk, or you could be a data engineer, and you start with the data. You receive data from an upstream process, so it's likely a data pipeline, and you do some exploratory data analysis and perform feature engineering, essentially getting kind of tabular or not so tabular data, unstructured data, and kind of molding the data into a form that a machine learning algorithm can be trained on. And this could be kind of things like normalization, standardization, doing some imputation, or it could be as interesting as generating embeddings and using those features alongside different kinds of other inputs to train this model. And also within this process, you would infuse domain knowledge into these inputs, because algorithms are mathematical constructs, but the trained model has to live in the real world and I suppose to solve real business problems. And there's domain knowledge that possibly cannot be encoded in the architecture of the model itself. Then you get to the point of model selection. The idea here is that you want to pick the best machine learning pipeline, including the algorithm, for the predictive task at hand from a space of different feature engineering approaches, multiple algorithm types and classes, and of course, hyperparameter combinations relevant to each of these algorithms. Then you validate the model on a number of criteria, like business requirements, of course, the model performance and regulatory requirements, and quite importantly, fairness and bias, which is very important in this day and age. And it always was important. Now we're finally getting the due attention to make sure that some machine learning models predictions isn't going to adversely affect the lives of people that are supposed to benefit from it. And finally, you put the trained model in production, and here there are multiple options that might be common, as well as not so common in industry. The most common one is we'll get into this in a minute, is batch inference or batch scoring. And the one that we see a lot of people promoting is real-time inference, like Dillon was alluding to. You get a model, you stick it in a web service, and you ping it whenever you want. But something that needs a lot of attention, I feel, is inference in stream, and the technology for doing that is more accessible than most people think. Regardless of how you deploy this model, after a while the model performance degrades, and you got to run the whole end-to-end lifecycle all over again. And this process is usually automated with human intervention in several key stages. Again, there are exceptions to this. For example, we're talking about online learning and reinforcement learning and so forth. But at a high level, you can think about the 95% of the use cases that you see in the wild. This is mostly accurate at a high level. So Dillon, could you go to the next? Thank you. All right. So let's take a look at batch inference, and the idea here is that this is the most commonly seen pattern of deployment, and this has been around for a long time. Especially I think the whole process of statistical learning was pioneered around the 60s, and since then this has been the go-to deployment pattern for traditional use cases like customer churn prediction, machine learning based forecasts. They're all relying on batch jobs that take a while to run, that run on a recurrent basis. Now here, the timeliness of the features is critical to make sure the models are trained on data that's representative of the current view of the world. So ensuring data quality across the entire pipeline from ingest to training is critical. Another thing that sometimes is overlooked is ensuring that pre-computed features that are served during inference are exactly the same as those used to train the model. And this is hard to do, right? it's kind of easy to do when you're doing batch inference, because both the training data pipelines and the inference pipelines could share some of the same infrastructure, but sometimes it's overlooked, and that leads to problems. And this issue is called commonly termed as feature skew. Feature skew is a big problem that's usually addressed by various engineering practices, and these kind of engineering practices and kind of constructs have been formalized into what is now termed a feature store. It used to be like kind of a set of best practice and abstract ideas, but now there's a thriving kind of industry of vendors and open source projects that solely focus on kind of this feature store idea, and you see it as a part of machine learning platforms as well. For example, Databricks has its own one. Now I'll hand it back over to Dillon to talk about streaming a bit more and streaming inference.
Yeah, we're actually going to start here and work backwards a little bit. So this is the same as the first one, with the kind of the key difference that now we want to have, basically it's essentially a pub sub, all right, publish subscribe sort of pattern. And I think this is what Avi and I both sort of agree, that this is the most overlooked. A lot of people will go straight towards, okay, I need this sort of request response version where I have the model running on a server somewhere. What this is saying is that instead of doing batch scoring, where I might have the model in like a Spark user-defined function or UDF, for example, I'm going to have that exact same thing, but I'm going to use a streaming framework here instead. And the key difference upstream of this is that now I have to have some sort of way to increase my feature freshness, right? So I need to also incrementally take new features, and potentially there might be some sort of feature store in here as well. Again, like I was kind of alluding to, that's sort of a talk on its own. But I think that the main thing to sort of appreciate here is going back to the example of fraud, and in sort of all use cases, as Avi saying, is that there's always going to be some sort of retraining needed if you choose this pattern. And ultimately, what that means is that the ability to have parity between your feature pipeline that you're using for training, which is usually batch, and the feature pipeline that you need for streaming, which is happening in production, actually needs to be the same. And so what we're actually seeing is that the most important aspect of a platform is sort of that ability to dial the knob of the latency that you need at the time you need it, right? Based on the business use case, based on what they're doing, you're doing retraining. And the reason why Spark is actually here in all of these is that Spark is a framework that has the same API for both batch and streaming. What we see here, I'm going to get a little bit deeper into streaming for a quick second. And I think the biggest surprise that most people have when we get into like, what's the actual textbook definition of streaming, at least how we define it in the context of Spark structured streaming, is that it actually has nothing to do with latency at all. Okay, the actual official definition, and this has been how we've sort of defined streaming since 2014 when we created Spark structured streaming at Databricks, is a stream process is unbounded. So in a traditional bounded process, I see all of the data at once. So if I need to do a stateful operation like an aggregation or a join or a window function, and window functions start to get really important when we think about detecting anomalies, right? We're looking at all of the data when we write that. So when I write a SQL query against any sort of database or data warehouse, I know exactly what I'm going to see at that point in time. And we don't usually think about consistency and isolation and all these problems, because many decades ago, we've already figured that out, and we have transaction logs and all these things. So we kind of take it for granted, right? We write the query and we see it. Now, in an unbounded world, I don't know if the data is coming in late. I don't know if the data is coming in out of order. I don't know if I've ever seen the full picture of the data, right? So, and when I do my aggregation or my join or my window, I never know for sure if there's going to be more data going in that belongs in some part of that state of that process. So what a streaming framework actually gives you, like the real value of streaming, is it gives you all of the guarantees and fault tolerance that you need to deal with that. And then it gives you tools in your toolkit, so to say, that allow you to handle state when you're doing some of those processes. And there's all sorts of implications around enriching data, around doing different kinds of windowing, whether it be rolling windows or tumbling windows or sliding or things like that. And really what this does is the fact that we can now handle unbounded data using those different tools and fault tolerance guarantees. That's why we're able to then reduce the latency as kind of like an end result, because we're processing the data incrementally. Okay. So, usually we take these things for granted, but with streaming, it's actually really hard. And the other thing that I think that we also take for granted is the ability to see kind of like this consistent view of the query. And this is actually the reason why I put lakehouse storage here and here. We're not just sort of throwing out lakehouse as a buzzword because we come from Databricks. There's actually a very good reason for this. With a data warehouse or a kind of traditional relational database, we can do the batch part just fine. Typically, there's obviously we can get into the challenges of hooking up a notebook and actually having like kind of native machine learning and all that. That's a different story. And then with a data lake, we can probably do the streaming a little bit more easy. But the problem is, as we're writing data in a stream, there's no sort of consistent or reliable way to read that data, right? So we might get corrupt files, we might get a lot of small files. And those are things that we take for granted, again, like ACID transactions and things like that we've had for databases. But when you want to be able to do streaming and batch on the same data without having to duplicate it, without having to deal with a lot of files all over your data lake, what a lakehouse storage format actually gives you is a transaction log. So I can be streaming data in, I can be logging all of my stream data from my production environment into some sort of monitoring system where I can kind of find feature skew and concept drift and things like that. And I can also be retraining off of the new data in production without having to duplicate it, right? So the lakehouse storage, the fact that it can unify both batch and streaming, and it gives you all of the fault tolerance and the guarantees that you need to do that, coupled with the fact that Spark gives you one API for both batch and streaming, kind of enable this architecture in a lot more kind of fluent way. That isn't to say that you can't use other streaming tools as well, like we have some kind of shown here, but that's sort of like why maybe Delta Lake and Spark simplify some of this. And oops. Now passing it back to Avi.
Thanks, Dillon. All right, finally getting to probably the most widely discussed serving mechanism in the machine learning community, and of course it's online serving. But as we kind of saw before, it might not be the de facto, or the best deployment approach for all kinds of use cases. It's great for some, but kind of looking at it from a kind of a practical point of view, it's important to understand that it's best for certain challenging use cases where where response is required, in as real time as possible with tight SLAs, and there's no constant flow of data, and they might happen at at any random point in time. So, for example, this is a good choice for use cases like real-time recommendations, where a person clicking on a button that might trigger a recommendation, might happen at a happen rather randomly. So it's still possible to kind of frame this in a streaming sense, where you kind of have a stream of inputs that hit a model, and you perform inference, and you kind of do some post processing. So it's always possible to, if you have sufficient throughput, it's always possible to frame this thing as a streaming problem. But for a lot of use cases where the occurrences that require a model inference is infrequent, online real-time serving is a good idea. And of course, for things like real-time object detection, this is obviously a very capable way of deploying the model. And typically, the way it's done in a production setting is that you deploy the model to either a large enough server that can handle the concurrency and the load, or as we see in a lot of modern projects, you deploy it to a horizontally scaling infrastructure, with something like Kubernetes or to a managed platform that handles that for you. And what's exposed to the client application is a REST endpoint that you can ping. But this is not the end of it. You have to make sure that this endpoint has to be ideally monitored by some real-time mechanism. Some people use Prometheus and Grafana. Again, if you use a managed platform, they have their own wrappers around it. But regardless of how you monitor it and how you deploy it, as in both the other inference scenarios, avoiding any kind of feature skew is super important, but it's challenging because you're serving features to both processes, both the training side and the inference side, in a manner that requires different SLAs, right? When you're supplying features for training, there aren't really tight SLAs because the model retraining cycles are rather lax. But when it comes to real-time serving and features, real-time serving and serving the features to facilitate the real-time serving, you have to make sure that feature serving is not a bottleneck for performing inferences. And there are a couple of ways of addressing this concern. And one way is to have parity between the two feature serving pipelines. And you can do this with something like kind of Apache Spark, because you have a unified API for both batch and stream processing. And of course, you can use Flink for the streaming side of things as well. But then again, the question of complexity comes in, and the complexity is not necessarily in a single axis saying that, hey, Flink is more complex than Spark or anything like that. It's just that you have to have an engineering team that has the skill set to kind of switch gears and work on these types of platform or frameworks for multiple aspects of the same machine learning architecture. But at the end of the day, you have to have the same feature calculation process for both the batch features and the real-time features that you serve. And sometimes people say it can be like similar, but no. If you want your machine learning output to be reliable, you have to make sure that the computations that you do to ensure the features are served accurately, they have to be identical. And again, having a unified API really simplifies the process, and you can have the feature serving for the inference side using a streaming pipeline directly, or you can have a streaming pipeline hydrate an online feature store using a kind of a NoSQL database or even a SQL kind of relational database, like say a MySQL database as the feature serving mechanism for real-time inference. So it's obviously more involved than the other two from that aspect, because if you kind of think about it, ensuring there's feature parity between training and serving for real-time serving using a REST endpoint also involves streaming. So if you're doing it right, this is a complicated architecture. But if you're kind of working with a static use case where you train a model once, like a large language model or something, and there's no real feature engineering or like running updates, yeah, then it's okay. That's probably a preferable way to deploy it. But for most other use cases, this gets hairy. If you can move to the next one, Dylan. Thank you. All right, so Dylan touched on this before, but I think, as usual, as is the case with me, I want to kind of take a step back and kind of clarify what these different kinds of drifts are. So concept, and Dylan touched on this, but essentially concept drift refers to a situation where the characteristics or properties of the thing we're trying to predict, like a fraudulent transaction, change over time. So fraud evolves, so the nature of fraud evolves. So it's important to understand what the drift in this target attribute is. Data drift, of course, means that the properties of the data used to train the model itself change over time. And another thing that we often don't consider is sometimes it's not really a drift, it's just bad engineering and just failure in upstream data pipelines that causes failures in downstream the machine learning process. For example, if you have a predictive maintenance model deployed, and somewhere in the upstream data sources, there's a software update, and you change the setting of how the temperature is encoded from Celsius to Fahrenheit, well, you're going to get different results. So it's really important to monitor the entire end-to-end process, and there's tooling to do that. And it's often the case you have to stitch things together, because kind of data monitoring and model monitoring are kind of handled separately. But it's also important to understand that there's no real monitoring of the model itself. You're monitoring input and output streams of data. So at the end of the day, machine learning monitoring boils down to a data monitoring problem, and tooling like MLflow, Delta Lake have a lot of features that can be used to put a system like this together. And of course, there are other rich open source projects like Evidently that are doing a great job of addressing certain aspects of this. So I know we have 3 minutes, and we can kind of move on to the next 2 slides, one after that, Dillon, because yeah. So one thing that I think is worth understanding is finding and kind of getting back to the kind of problem of fraud. Finding anomalies in unlabeled data is a well-established discipline, right? Like this has been done for a long time. Fraud detection has been a thing, a traditional approach for a long time, and there are various unsupervised machine learning algorithms like isolated forests and more modern ones like deep support vector data description, which is obviously neural network based, that have proven to be very effective. But this is typically applied to structured data. But with the explosion of deep learning recently, you can kind of think big and apply this same mechanisms to finding anomalies in embeddings. And especially with things like image bind, where you can have multimodal embeddings, kind of multimodal data projected to the same embedding space, you can essentially perform anomaly detection on multimodal data all at once instead of having disparate pipelines. So this field is ripe for it's ripe for innovation, and a lot of interesting things are going to come out of this. So Dillon, you wanna?
Do you have time to look at the demo, some of the code that we wrote, probably, or do we want to just think we cut?
We have 2 minutes.
Well, I think I'll leave this up. Maybe we do the QR code and people can kind of take a look. And then we also have a blog that we put out on the ODSC website about exactly what Avi was talking about around using embeddings to find anomalies, and then combining that actually with Spark structured streaming to do, to actually do that in a sliding window. And there's also some more examples that we have here that are actually a little different. But Avi, I think maybe we